Can I go on to speak? I will.
Sorry. I think, yes, you can continue, Professor Inokawa. So please, the audience, please turn off your microphone, please. Thank you. Please go on, Professor Inokawa. Thank you.
And I will explain the operation principle of the proposed device. That is a suspended wire resistor to evaluate the thermal conductance kappa and also heat and capacity. And then I will show you the experimental results based on DC direct current measurement and also the frequency response measurement. And then I will introduce the latest result of the real-time measurement of these thermal parameters. And I will end up with a short summary. As is well known, thermal analysis of material is widely used. For example, differential thermal analysis can detect the many kinds of physical and chemical changes, such as melting, evaporation, sublimation, absorption, desorption, and also chemical reaction like decomposition and oxidation, and so on. And it is widely used and established, and also there is a very nice measurement equipment. But there is an issue for the use of such analytical tool for real-time sensing of the environment because it has a large footprint and also consume high power, and also response is rather slow because the measurement equipment have to sweep the temperature. So there is a lack of real-time operation. And the solution I would like to show is the use of a micrometer size resistance thermometry. And for the real-time measurement, I also propose the use of a thermal feedback oscillator. First, I would like to explain the operation principle of the resistance thermometry. And this slide shows the structure of the devices used in the resistance thermometry. Here, there is a wire, suspended wire made of metal, and it has 4 terminals, current terminals and voltage terminals. And we can precisely measure the change of the resistance by making use of the 4 terminal configuration. And this wire is suspended in air and thermally isolated from the substrate. In such case, all the heat flows in the direction of wire, so we can have a rather beautiful analytical solution for the temperature rise and also the resistance with respect to the temperature. And the good thing about this device is that we can simultaneously heating up the wire, and also we can measure the temperature of the wire by measuring the resistance change. And you can see from this cross-sectional view, and this wire is suspended in air because there is a cavity inside the substrate. And when we would like to analyze some material, we will put analyte. In this case, porous silica is analyzed, such analyte is attached on top of the metallic heater. In this case, titanium is used as a heater. And when we measure the resistance with respect to the square of current, we can see the straight line. And this slope is correlated to the temperature coefficient of resistance and also the thermal resistance of the wire. And this is a very simple, and also the solution can be obtained accurately by analytical method. And when we would like to look into the heat capacity or thermal capacitance, we are going to measure the frequency response of the resistance. And for example, if we drive the nanowire by alternating current of frequency f, temperature oscillate like this with this amplitude if the frequency is rather slow. But if the temperature, if the frequency becomes higher, this amplitude, the temperature amplitude becomes smaller because thermal response determined by the thermal resistance and thermal capacitance is rather limited. For example, when there is a cut frequency is at the cutoff frequency, and the amplitude becomes 70% of the original amplitude. As the frequency becomes higher than the cutoff frequency, there is almost no temperature fluctuation. Only the temperature distribution exists like this. And the temperature temperature amplitude of the nanowire can be measured by looking at the third harmonics of the voltage across these voltage terminals. So when we change the frequency of the driving current, we can get the characteristics like this. We usually define the cutoff frequency where the amplitude becomes 70%, and also the phase delay over 45 degree. And it is also shown that this cutoff frequency is correlated to the specific heat Cp and also the thermal conductance with this equation. So by measuring the cutoff frequency, we can detect the specific heat or thermal capacitance. And actually, this parameter, specific heat or thermal capacitance, is also the physical or chemical phenomena that can be detected by the ordinary thermal analysis, like differential thermal analysis. And for the verification of this operation principle, we fabricated the device like this. And you can see that there is the titanium heater, and this titanium heater is supported by the silicon dioxide thin film. And on top of the titanium heater, an analyte material. In this case, porous silica is used as an analyte material. The reason why we chose porous silica is that we can observe the absorption and desorption phenomena of many kinds of volatile gases. And by changing the temperature of the sensor, we can get a specific spectra of absorption and desorption. So we are intending to detect the volatile material in the atmosphere. And the titanium heater, I'm sorry, this platinum is not correct. This layer is the thickness of the porous silica. And there is a titanium heater. A titanium heater is useful because titanium has a small thermal conductance, and we can get rather higher temperature rise. And in order to extract the thermal parameter of porous silica, we made a variation in the width of this nanowire. And this slide shows the DC direct current measurement of resistance with respect to square of the current. Because entrance power, heating power by the current is proportional to the square of the current, and also the change of the temperature is reflected to the change of the resistance through the temperature coefficient of resistance. Therefore, we can get a nicely straight line with respect to the square of the current. And by looking at the slope of this curve, we can find out the thermal conductance of the wire. If the thermal conductance is low, it is easy to get a higher temperature rise. That's why the resistance becomes higher rapidly. And if the thermal resistance is small, it is rather difficult heating up. That's why the slope becomes gentle. And this line corresponds to the structure with porous silica. And this line corresponds to the case without porous silica. Due to the addition of porous, conduction becomes larger and the slope becomes gentle. And based on this information of slope, and also by changing the width of sample, we can extract the thermal parameter of only the porous silica part. By comparing the cases with and without the porous silica, we can find out the thermal conductance of 0.67 watt per meter Kelvin for the porous silica material. And this is 48% of the thermally grown silicon dioxide. Probably due to the porosity of the porous silica material. And this slide shows the frequency response of the temperature fluctuation. And you can see that the temperature fluctuation gradually decreases, and the decrease of the temperature is one order for the change of one order of frequency. And from this curve, we can find out that the cutoff frequency for the cases of titanium only wire is 161 Hertz. And also the wire with porous silica has a slightly lower cutoff frequency of 143 Hertz. And based on this graph, we can find out the heat capacity. This heat capacity is a heat capacity per unit length. By taking this as a function of wire width, we can get a linear relationship like this. And by comparing the slope of both cases with and without porous silica, and we can extract the heat capacity of a specific heat of a porous silica of 9 times 10 to 5th joule per Kelvin cubic meters. And this value is 56% of the thermally oxidized silicon dioxide. Again, this is probably due to the porosity of silicon porous silica. And in the next step, in order to realize the real-time measurement of thermal conductance and the specific heat, we tried with the thermal feedback oscillator. As I explained, when the driving frequency of the heater becomes high, temperature fluctuation of the heater cannot follow the rapid change of the alternating current. And as a result, there is a phase delay between the temperature fluctuation and the driving AC current. And this thermal feedback oscillator lock the phase delay to 45 degrees. So this thermal feedback oscillator oscillates at the cutoff frequency where the phase delay by the suspended wire device becomes 45 degrees. So by utilizing this kinds of a device, we don't have to rely on the sweep of temperature. So we can make a real-time observation of thermal conductance and the heat capacitance. And at this time, in order to verify the operation, we change the pressure of the environment of the device.
Excuse me, Professor Inokawa. Excuse me, sorry for disturbing your lecture, but you have just 3 minutes in this your presentation. Three minutes.
Okay, but this is almost the last slide.
Okay, thank you. Sorry.
And by changing the ambient pressure, we can change the thermal conduction. That's why when the pressure becomes larger, cutoff frequency becomes lower. But the change of the cutoff frequency is rather small because you can see that there is almost overlap between two lines. But as the wire length becomes larger, change of the cutoff frequency due to the pressure change becomes larger. And we can successfully do the experiment of a thermal feedback oscillator. And this is pressure on the horizontal axis, and we can detect the linear relationship of oscillation frequency with respect to the pressure. And in summary, I here propose to use the suspended wire resistors for the purpose of thermal analysis. And by comparing the wire with and without porous silica, and we could extract the thermal conductance of 0.67 watt per meter Kelvin, and also the specific heat of 9 times 10 to 5th joule per Kelvin cubic meter. And we also could successfully show the operation of thermal feedback oscillator, and that could be that could realize real-time sensing operation. Thank you very much for your kind attention.
Thank you very much. for your very nice lecture and very interesting study and also challenging work, I think. Thank you very much. And now the lecture is open for question and discussion. Is there any questions from the audience? Not yet. So I would like to ask one thing. Professor Inokawa, you prepared the microstructure to measure the heat capacity of the porous silica, and in that case, how did you prepare that structure? I mean, uh, the sample should maintain the original state, but the structure should be very small. I think it's very difficult technique. If it's possible, then could you introduce a little bit about how you prepared that structure?
Yes, and the fabrication process is based on the ordinary planar process for integrated circuit, and that together with cavity etching inside the silicon substrate.
I see.
We carefully prepare, handle the material so that the characteristics is not to change during the fabrication process.
I see. Yeah, thank you very much. And I would like to ask another thing. Is there any limitation or some threshold or about the thickness of the porous silica? If that is too much thick, then maybe there will be some temperature distribution. But if that is too much thin, then maybe it's very difficult to measure the heat capacity. So what do you think? Is there any good thickness for measuring the heat capacity of the porous silica?
Thank you for the question. And the suspended wire consists of a heater and the supporting silicon dioxide layer. And on top of that material, analyte material is attached. So, heater material and also supporting material also conducts heat and also has a heat capacitance. So if the heat capacitance or heat thermal conductance of analyte becomes much smaller than the parameters of heater or supporting material, we cannot detect the change. So there is some limitation in the thickness of analyte material.
Thank you very much. I think that is very challenging and it's very difficult work, but you successfully obtained the very good result and also the very good fitting line, and I'm so surprised.
Yeah, so, thank you for your comments.
Thank you. So is there any other questions from the audience? If not, then it's almost the time to move to the next lecture. So it's okay? Okay, so thank you very much, Professor Inokawa again. Thank you very much for the great work. Thank you. Okay, so shall we move to the next lecture? Professor Kondo. And yes, thank you. And before that, I'd like to a little bit introduce Professor Kondo. He got many awards, and one of them is on 2019. He was awarded the 16th International Conference of Quality in Research Best Paper Award, integration of localized surface plasmon response, resonance, and electrical sensors for liquid environmental monitoring. Sorry. So could you start, Professor Kondo, could you start the lecture?
Yes. Could you see my slide?
Yes, yes, we can.
Thank you very much, Mr. Chairperson, for nice introduction. I also thank to organize the committee for inviting me this symposium. My name is Jun Kondo from Shizuoka University. Title of my presentation today is ultrasonically assisted tunable localized surface plasmon resonance and its multi-sensor application. This is a joint research with Shizuoka University and the University of Indonesia. This is the outline of my talk. In my laboratory, we have investigated sensors and actuators using surface waves. One surface wave is acoustic or ultrasonic surface wave. We say surface acoustic wave. This is for sensor and actuator application. The other is localized surface plasmon resonance. Before we had investigated surface plasmon resonance. Surface plasmon resonance is propagating surface wave, optical surface wave. But local surface plasmon is not propagating wave. It's located around the nanoparticle. Today's my presentation relates both phenomena. So at first, I briefly introduce both previous research. Surface acoustic wave soul propagates on an elastic material surface. Where a piezoelectric substrate is used, the soul can be electrically generated and received due to the inverse piezoelectric effect or piezoelectric effect. For this purpose, we have utilized interdigital transducer. The soul devices have been widely applied for the filters and antenna deflectors for the mobile communication system, such as smartphones. In recent smartphones, more than 10, around 40 acoustic wave devices are involved as an antenna deflector, including the soul device. But in our laboratory, we apply the soul devices for sensors and actuators. There are two typical modes of the surface acoustic wave. One is a rarity type surface acoustic wave, or simply so, and the other is horizontal surface acoustic wave. Propagating modes are different. And the propagating mode depends on the piezoelectric material, because these materials are materials. So propagating mode depends on the crystals and orientation in the crystal. These crystals is very, very popular for generating rarity type surface acoustic wave or SHO. Using these surface acoustic waves, we have investigated sensors and actuators. For sensor application, we use RARISO or SHO. RARISO is for gas sensor application, and SHO is for the reflect phase application for monitoring these properties, physical properties. That means the physical sensor application and also biosensor application. And others application based on the physical property detection. In these applications, the environmental monitoring is very, very important. For example, as you will know, the SDGs, in SDGs, goal 6 is relate safety water for drinking water. And using our sensor, it is possible to detect the water quality. Later, I briefly explain introduce the result of the water measurement. And also, this application is also important. That is a nonlinear acoustic application. That is a actuator application. I also introduce this application. First, let me show you the result of the water measurement using SHO sensor. The SHO sensor can detect the conductivity and relative permittivity of the solution at the same time. And the horizontal axis is velocity change of the wave, and vertical axis is attenuation change of the wave. We measured several kinds of commercialized mineral water, and also these are Japanese water, and these are from Europe. And you can see that the SSO sensor can detect the difference of the conductivity and permittivity of these samples. And also, we measured Hamamatsu tap water. It's located here. The permittivity of this Hamamatsu tap water is little difference between the commercialized natural mineral water because something material are involved. That material depends on the quality of the water, and also it's decided by the Japanese law. And we measured this water around 200 days, but all the measured point locates around almost same area. So if something materials is mixed into the water, maybe the conductivity or relative permittivity will change. So it is possible to measure the some material in the water sample, and also this is the application for the to quality of the water or safety check the water. That is one application of the SSO sensor. So please remember, using the SSO sensor, we can evaluate the relative permittivity. This is a nonlinear acoustic application of the SAW device. We applied sinusoidal signal to the interdigital transducer and generate surface acoustic. Then this droplet, water droplet, is manipulated to the SAW propagation direction. When applied, we increase applied electrical power, small droplet is ejected from the liquid. And when we keep the thin water layer on the surface, very, very small water drop, that is mist, is generated. Diameter of the mist is around 1 to 2 micrometer. The other application is integration of the sensor on the manipulation surface. In this case, interdigital transducer is used as electrochemical sensor for detecting liquid impedance, and the water droplet is manipulated and mixed and measured impedance change. So using SAW, quickly mixing is realized. However, if without SAW case, it is at least 10 minutes needed to obtain the saturation value. Therefore, to use a SAW is very, very important for the small droplet manipulation and mixture. Next is a localized surface plasmon resonance. The LSPR application is all in this symposium. Several keynote speakers explained about the plasmonic effect. That is a very interesting optical characteristic of the metal nanoparticles. And we have utilized gold nanoparticles, aurum nanoparticles for the sensor application. For sensor, the aurum nanoparticles are fabricated on the substrate, for example, a glass substrate. And then monitoring the transmission light or reflected light, we can know the difference of the reaction of something. And the LSPR spectra depend on the numbers of the and shapes of the aurum nanoparticles and the distance between the particles and the refractive index on the aurum nanoparticles. Therefore, using the LSPR sensor, we can detect the refractive index around the nanoparticle. In previous research, we summary annealed to fabricate the aurum nanoparticles. After cleaning the substrate, thin gold film is evaporated onto the glass substrate like this, and then this glass substrate is annealed at around 400 degrees Celsius. Then aurum nanoparticles are obtained. In conventional method, the annealing time is very, very long, like this, and cooling is a natural cooling. However, we found the short annealing and quenching is better than the long-time annealing and cooling. For example, this is a typical result of the comparison result of the long-time annealing and natural cooling. And this is a short-time annealing and quenching. After annealing, the LSPR spectra become the very narrow, high Q quality factor. And the result for the long-time annealing and short-time annealing is almost same. And also we measure the change of the peak wavelengths using the ethanol solution. These results are from the long-time annealing and natural cooling, and these results are from the short-time annealing and quenching. The shift of the wavelengths for the short-time annealing and quenching is bigger than the long-time annealing and natural cooling. Therefore, the refractive index sensitivity for the short-time annealing and quench is better than the long-time annealing and natural cooling. Based on these results, we want to integrate all nanoparticles on surface acoustic devices for the following applications. First one is to realize the tunable localized surface plasmon resonance. Second is multi-sensor for simultaneous detection of the several physical properties. And third is microfluidic system to monitor the refractive index change. But today I'm talking about these two topics. I already explained there are two types of the surface acoustic waves. One is Rayleigh surface acoustic wave, and the other is the shear horizontal surface acoustic wave. If we fabricate the all nanoparticles, the motion on the surface of the particles are different. For the Rayleigh surface acoustic wave propagates right-hand side to left-hand side. The particle motion is like this. This is due to the trajectory of the particle displacement profile of the wave. And for the SH wave like this. And in this research, we choose the SH soul and we fabricated all nanoparticles on the SH soul device. Before talking about the experimental result, I show you the result of the simulation result of the plasmonic electric field. This simulation was done using a software of CST Studio 3D EM simulation. The semi-sphere or gold nanoparticle is on the lithium tantalate surface, and this is a single nanoparticle, and the others are dimer case. And we changed the distance between two particles. One is 1 nanometer, and the other is 5 nanometer. When the 1 nanometer case, very strong E field is generated between the two particles. Compare the other results and increase the distance, the electric field decreases and there are no coupling between two particles. We also calculated scattering, extinction, and absorption for the small particles using these equations. And this figure shows the absorption result. We changed the distance between two particles, gold particles on lithium tantalate. This is the distance between the particles, and the horizontal axis is wavelength, and vertical axis is absorption. And these numbers show the peak wavelength and absorption. And please pay attention to the wavelengths. The increasing the distance between particles, the wavelength decreases. That means the blue shift occurs with increasing the distance of the particle. Okay, so please remember the blue shift occurs when the distance increases between particles. Then we fabricated the all nanoparticles on SHSO device. Firstly, the SHSO device was fabricated using 36YX lithium tantalate single crystal. Using the conventional lithography technique, we patterned the IDT and provocation surface and IDT. The electrode materials are gold and chromium. Thickness of gold is around 200 nanometer and chromium is around 10 nanometer. After fabrication of the SHSO device, gold thin film is evaporated, only the propagation surface. Then the whole device was annealed at 500 degrees Celsius and for 5 minutes, and then quenched, minus 40 degrees Celsius per minute. The quenching is short time annealing and quenching is better for the SO device because we have narrow electrode finger here. If the annealing time is long, this electrode is damaged. Therefore, short time annealing and quenching is better for the SO device and the integration of the all nanoparticles on the SHSO device. And this photograph shows the actual device fabricated. This area is a gold thin film area, and all of nanoparticle exist around here. And this part is propagation surface of metallites, and this area is a crystal surface lithium tantalate directly contact with the all nanoparticles. Using atomic force microscope, we observe the surface morphology. From this figure, it is very difficult to understand the difference, but from the magnified figures, please compare this figure and this figure. You can see the particle size increase due to the short time annealing and quenching. And from the 3D result, we counted the numbers of particles and results shown here. The small all nanoparticles decreases, and the average diameter of the all nanoparticle is around 10 to 20 nanometer. So this is one effect of the short time annealing and quenching. And also, we measure the fundamental spectra before and after annealing and quenching. The before annealing, the full wide half maximum is wider than the after annealing and quenching blue result. Then we measure the interaction of the SHSO and the LSPR using this experimental setup. White light is used as a light source, and reflected light is measured in this spectrometer. And so for generating of the surface acoustic wave, we use a signal generator. The frequency was 50 megahertz and observed using oscilloscope. Also, we used a network analyzer to evaluate the fundamental characteristics of SHSO device. This is a result of the frequency characteristics of SHSO. Due to this is a frequency versus transmission coefficient. Due to the all nanoparticle fabrication of thin gold film evaporation, the insertion loss increases and before and after. But there is no significant differences observed with and light on case and light off case, almost same. Therefore, from this result, we concluded there's no coupling between the localized surface plasma and SHSO. In other words, SHSO is not influenced by the LSPR. Next, we observed the LSPR spectra using 3 devices. We fabricated 3 devices. And off means without SHSO, and on means with SHSO. And from this figure, you can see the peak wavelength slightly decreases due to the SHO excitation. That means that due to the shear horizontal vibration, the particle on the surface is moved and distance is changed. And compared with the simulated result, the distance between the particles increases. Therefore, wavelength of the peak wavelength decreases. That is the blue shift. Then we evaluate this spectrum. Normally, FWHM is used to evaluate, but evaluation, however, from this result, it's very difficult to obtain the FWHM, so we define the full wide 3/4 maximum FWTQM. And the blue result of this figure shows the FWTQM. And off without SHO and on is with SHO. With SHO, the FWTQM increases like this for all devices. And also, we obtain the Q factor. Q factor is obtained the lambda p. Lambda p is the peak wavelength is divided by FWTQM. And the Q factor decreases due to the SHO. And therefore, from this result, the peak shift is moved due to the SHO device. Therefore, SHO shear horizontal vibration. Therefore, tunable localized surface plasmon is realized using the SHO device. Also, we checked the sensor characteristics of the LSPR with and without SHO. And this figure shows the change of the peak wavelength and reflectance at water or 100% ethanol. And we varied several voltage of the SHO, applied signal for the SHO. And you can see that also decreased the wavelengths. That means the blue shift. For the sensor application, we want to know the difference of the wavelength shift between the water and the sample. And the results shown here. Horizontal axis is the refractive index of ethanol solution, and the vertical axis is a wavelength shift. But we cannot observe any significant difference between the on condition with SHO or off condition without SHO. Therefore, for sensor application, the shear horizontal vibration is not influenced because the shear horizontal vibration not influenced to the refractive index of the solution. Therefore, for sensor application, there is no influence of the SHO vibration. Next, we also measure the velocity shift of the SHO for using the same solution, ethanol solution. And the result shown here, this result is SHO without oram nanoparticles, and red and blue are with oram nanoparticle, but light off case or light on case. There's no difference between the light off and light on case. Therefore, there's no interaction between the LSPR and SHO. However, we found increased sensitivity with and without the oram nanoparticle. That is the increase of the velocity change is the influence of the surface roughness due to the oram nanoparticle fabrication. Why such sensitivity increase occurs? To discuss about this result, we measure the time response of the SHO. This is the input signal, and this is the received signal. And found phase velocity with oram nanoparticles layer on surface is faster than the without case. So velocity increase occurs with the very thin gold oram nanoparticle layer on lithium tantalite. But we have not clarified the mechanism increase of the velocity. But this is also important result for us. Okay, finally, I conclude my talk. So all of nanoparticles are fabricated on lithium tantalate surface and ultrasonically vibrated. The blue shift of the resonance wavelength is observed due to the shear horizontal vibration of the SHO. Therefore, tunable localized surface plasma resonance is realized on the SHO device, but SHO is not influenced by LSPR. Also, for multi-sensor application, we measured ethanol solution. For the LSPR sensor, the change of the resonance wavelength is not influenced by the shear horizontal vibration. For the SHO sensor, the velocity change increases, but this is not influenced by LSPR. That's the influence by the surface roughness. Then, based on these results, we conclude multi-sensor is realized for detecting refractive index and refractive permittivity at the same time. Thank you very much for your kind attention.
Thank you very much, Professor Kondo, for your very nice talk and also sophisticated your work. I'm very impressed. Is there any questions or from the audience? If not, then I would like to ask a little bit something. I'm very much interested in your work. And first, from the AFM mapping, AFM image of the gold surface,
Yes.
After the annealing, the particle became larger.
Yes.
And I feel like that not only the particle size, but also the shape is becoming a little bit more cubic compared to the before annealing. And I'm not sure, but such structure may affect the SAW device factors, or what could you give some
Yes.
comments on this?
Yeah, actually, we cannot control the structure of the particle after annealing, during the annealing. So this part, the not hemisphere, but some part is the other like structure. So the structure is not uniform.
Huh.
Yeah, but of course, this structure is dependent on the LSPR characteristics. Therefore, we need more research by changing the annealing time and also quenching rate to fabricate the. We want to realize a uniform structure fabrication. Therefore, optimization condition is to clarify the optimization is necessary.
I see. Thank you very much. And any other questions? Otherwise, I would like to ask another question regarding this particle. I believe that you mentioned that if you slowly cooling down, then that also affects some difference in the performance of the SAW device, and how the slow cooling affect to the particle size of the gold. I think that particle size becomes much larger, or
yes, the particle size is this spectra depend on the particle size. In our measurement, that from the 10 to 20 nanometer is the best. And therefore, the quenching and short time annealing is better for us. Of course, but for the long time annealing, and we don't try the long time annealing and quenching because the glass substrate is damaged.
I see. Okay, thank you very much. And any other questions? No? If not, then it's almost that time, and I would like to move to the next lecture. And let's thank you very much, Professor Kondo, for the very nice lecture. Thank you very much. Okay, so let's move to the next lecture. The next lecturer is Dr. Akhilesh Babu Gangan Boina. Is this correct?
Yes, Professor.
Okay, thank you. So the lecture title is the electrocatalytic water oxidation based various virus sensing. Okay, so please start the lecture.
Okay, sure. So let me share my screen. So, Professor, is my screen, are you able to see my PPT now?
Yes, yes,
okay.
I can.
Okay. So let me begin. So first of all,
sure.
Very good morning to all the participants from India and a very good noon to all the participants from Japan here. It is my great pleasure to give a talk in this conference of ICONN 2021. I have been following the conference since last 2 days, and it's a really big conference, and really appreciate the SRM University team for such a good organization of this conference. Okay, let me start my talk. So the title of the today's talk would be Electrocatalytic Water Oxidation Based Virus Sensing. So our group majorly works on virus sensing. So we develop various virus sensing platforms using the various nanotechnology based approaches. And coming to the virus sensing, I don't think it doesn't need an introduction in the present scenario of this ongoing COVID pandemic, because everybody, even the layman without the knowledge of any science, understands the importance of what a virus can do, like how, and also how important is virus sensing. Like during the last pandemic of COVID-19, everybody knows what is an RT-PCR test, what is an rapid antigen test. Like every layman could get the knowledge of this because of the drastic effects, and everybody in the world, in some or the other way, have been affected by the COVID-19. So let us get into the introduction now. Coming to the detection of this COVID-19, a COVID-19 or come to any virus. So basically the gold standard which is followed even today and from several decades is the RT-PCR method, in which the nucleotides are amplified several times and detected. But however, as all of us also clearly know that this process is very tedious, very laborious, need a lot of expertise, I mean human or manual expertise, and also time taking as well as expensive. So one of the reasons why COVID pandemic is being even not easily controllable and traceable, because we are still dependent on the RT-PCR test for the COVID-19 diagnostics, which takes very long time for the diagnosis, as well as immediate detection is not being able. However, with the advent of this nanotechnology in the recent decade, in the last decade, several other methods trying to replace the RT-PCR, though they haven't existed yet, but which are been trying to replace this RT-PCR are currently being developed. Like some of the technologies, like if we can see the SIRS technology, which is the surface enhanced Raman spectroscopy. So here in the SIRS based technology, it is very clearly using the Raman signal, of some nanomaterials, depending upon the virus concentration or whether the SIRS signal can be enhanced or decreased. Based on this, the SIRS-based virus sensors are developed. Similarly, there are like all of us know the rapid test, which has been already developed and also presently used in several countries for COVID-19. That is the LFSA, lateral flow assay, in which antigen detection is being possible. But however, the reliability of this method is still not very proper. That is the reason several countries are still only depending on RT-PCR. Like if we presently want to travel from one country to another country, we must carry an RT-PCR negative certificate, though there are several other technologies like lateral flow assay or others are already available. And coming to this, there are some other technologies like fluorescence based on LSPR methodology, which we got a very detailed information about the principle and methodologies which are following LSPR from our previous talk. And getting into few other technologies like electrochemical and calorimetry. So these are the various, some of the various methodologies being available, are being developed for the virus sensing. So here presently in this laboratory in Shizuoka University, I have been developing, working on the fluorescence, electrochemical, and calorimetric. The left three parts, I have been working on these three these three parts of the for virus detection. And now coming to the detection, fluorescence or electrochemical or calorimetry, this individual method has its own advantages, at the same time disadvantages. So what we have done is we have tried to combine two different methods into one detection technology. Like in one detection technology, if we can get two different kind of signals, we are following the same procedure, but if we can get two different kind of signals, then the reliability of the detection system can increase, or we may meet equivalent to RT-PCR. I'm not sure we can meet, but we are just trying for achieving this. So what we have done is we have tried to develop a combination of either fluorescence or electrochemical or calorimetric or electrochemical methodologies. Getting into the developed methodology, so let me get into the details of the methodology. So here, this is one of the recent work which we have developed for the dual modality detection based virus detection. So coming into the concept, what happens is the nanoparticles which are developed are having both magnetic property as well as fluorescence property. So depending on the nanoparticles fluorescence intensity as well as some electrochemical signal generation, we have developed two different methodologies for virus sensing. Like, let me explain the methodology follows. So before getting into the methodology of virus sensing, I'll explain you the new method we have developed for the preparation of the nanoparticles. So first we have prepared the quantum dots. These quantum dots are fluorescent. Now on the surface of the quantum dots, we have done the iron nucleation. So iron shell is grown completely on the surface of the quantum dots. After the complete growth of the iron shell, we have done the controlled oxidation. When the controlled oxidation has occurred, the solid iron shell has become hollow. So some void, some space has been created between the quantum dot and the iron shell, because of which the fluorescence intensity of the quantum dot was maintained. Like in this stage, when the iron is in completely contact with quantum dot, the fluorescence intensity was completely quenched. However, when the void is created, the fluorescence intensity is coming. So this prepared nanoparticle is having hollow iron shell, maintaining the magnetic property, as well as quantum dot inside maintaining the fluorescence property. So after the successful synthesis, we have characterized with various methodologies, various technologies, like initially like using the TEM, where we can see the quantum dots prepared were very circular and around 7 to 8 nanometers in size. And later, when the iron shell is grown on the surface of the quantum dots, we can clearly see the complete iron shell grown on the surface of the quantum dots here. Later, after the controlled oxidation, the space has been created between the quantum dot and the iron shell, which can be clearly observed in the HRTEM image. So this characterization successfully proves the nanoparticle has been prepared. Now further properties, like when a magnet is placed, all the nanoparticles were separated. At the same time, under UV light, the fluorescence has been moved. So this further confirmed the preparation of the nanoparticles. Then for the further characterizations like XRD, XPS, and magnetic moment were analyzed to measure to characterize the functional groups and further properties of the synthesized nanomaterials. Now, after successful synthesis of this beautiful hybrid nanomaterial, we developed a methodology for the virus detection. So using these hollow magnetic nanoparticles, which are encapsulated with quantum dots, based dual modality virus detection has been performed. So coming to the methodology, first, what we have done is that for the prepared quantum dot, for the prepared nanoparticles, we have conjugated the antibody initially. This is the first step. Then we have also taken a gold electrode on which RGO was deposited and antibody were coated. So these were the two precursors which have been prepared for sensing. So this antibody is which is coated on the surface of either the nanoparticles or RGO electrode, is respective to the virus which needs to be detected. Now, what we have done is initially we have took the virus solution and mixed it with the prepared antibody conjugated nanoparticles here, mixed and allowed to conjugate. The antibody conjugates with the virus. Now, when a magnet is placed over the container, all the nanoparticles along with the virus conjugated nanoparticles are separated. And this solution containing various unreacted or serum matrix has been separated. After then, these only nanoparticles and virus conjugates have been redispersed into buffer solution. And this RGO antibody-coated RGO electrode was immersed into this solution. Here, what happened? Further attached to the antibodies and formed a sandwich structure. Like first is the electrode with antibodies hanging, and then virus attached. To the virus, several quantum dots have attached. Now, when the virus and quantum dots have attached, they have been separated. So when this electrode is separated from these solutions, along with the virus, several quantum dots have been removed, have been separated. So several virus particles have attached to the surface of the electrode. So with the attachment of the virus particles on the surface of the electrode, the conductivity of the electrode is continuously decreasing because of the conjugation of the agio is very conducting. But when virus is attached, virus is a big size particle. When virus is attached, the biological membrane is interfering the electrochemical interaction, interfering the electron transport. Therefore, the conductivity is decreasing, which can be measured using the electrochemical impedance. So more is the concentration, the more would be the charge transfer resistance created. So using this methodology, one sensing could be obtained with respect to virus concentration. At the same time, when the electrode is removed, along with the virus, the conjugated quantum dots have also been separated. That means the concentration of the quantum dots in this solution is continuously decreasing. So the concentration of this quantum dots is decreasing along with the virus. When more is the virus concentration, so more quantum dots will be attached and separated. So using the same solution, we could further use the fluorescence modality. So we could obtain both electrochemical signal as well as the fluorescence signal using the single methodology developed. So after several optimizations of the concentration of nanoparticles, antibody, successful conjugations, and various parameters optimizations, we have conducted the sensing using the HEV like particles, and we could see when the particle HEV virus like particles concentration increased from 10 femtogram to 10 nanogram per ml, the electrochemical impedance values consistently increased. The charge transfer resistance consistently increased. For which we can get a beautiful calibration curve with respect to using the concentration of virus-like particles and the change in the charge transfer resistance. This is using one modality. Similarly, when the virus concentration has been increasing, the fluorescence of the remaining solution is continuously decreasing, through which further we could establish a second calibration curve. So using this single modality, I mean the single method, we could get the two different signals. So the developed method was successful, and we have also performed the method in some real sample detection and further. And the selectivity of the method was very high because the selectivity is completely dependent on the antibody conjugated. So this method was applied for HEV detection, norovirus detection in clinical samples, as well as the laboratory prepared HEV or norovirus like particles. Now, after finishing this work, we thought that though dual modality here is advantage for double comparison, I mean confirming the data for 2 times, but further we wanted if we can extend the calibration curve wherein we can see more sensitive detection could be possible. So for this approach, we further developed another methodology, that is dual modality detection of norovirus using V2O5 nanoparticles encapsulated liposomes. So in this method, we have used liposomes for the as an amplification platform. So what we have done is, initially we have synthesized the V2O5 nanoparticles, which are known redox nanomaterials. These V2O5 nanoparticles were encapsulated inside the liposomes. So each liposome consisted several V2O5 nanoparticles, several hundreds of V2O5 nanoparticles. Now, after successful encapsulation, these liposomes were conjugated with antibodies of interest. So in this case, we have conjugated with norovirus antibodies. Then at the same time, we have prepared some magnetic nanoparticles to which again antibodies were conjugated. Same antibodies were conjugated. Now in the virus sample, we have immersed these liposomes, conjugated antibodies, as well as the magnetic nanoparticles. So upon incubation, what happened? The antibody present on this magnetic nanoparticles as well as the liposomes conjugated together, and they formed a sandwich-like structure. So liposome, virus, and magnetic nanoparticles. Now further, because magnetic nanoparticles are conjugated, the matrix effect is very important in sensing to reduce to increase the selectivity or sensitivity of the methodology. So after the conjugation of these sandwich structures, they were magnetically separated. And after magnetically separating these structures, the separated liposomes, which increased it, like more the virus concentration, more liposomes were separated. Now these separated liposomes were broken using the tritonics to release the encapsulated V2O5 nanoparticles. So these V2O5 nanoparticles, which were released from these liposomes, helped for the determination of the optical signals, that is the oxidation of TMB, using in the presence of H2O2. So TMB was oxidized oxidized and blue color was developed. At the same time, these released V2O5 nanoparticles also had some electrochemical signals. As they are both electrochemical and redox active materials, they could generate, V2O5 could generate some DPV peak. So when deposited onto the electrode and measured the DPV, the peak concentration increased with respective to virus concentration. As virus concentration was increasing, the number of released V2O5 particles were increasing. So the current value has been consistently increasing. So again, after developing this methodology, several optimizations have been done, like the concentration of V2O5 incorporated inside, then the concentration of antibody to be deposited, and the time duration for the incubation. So after several optimizations of the developed methodology, we have performed the sensing performance, wherein we could see that when the norovirus-like particles concentration increased from 10 femtogram to 500 picogram, the electrochemical modality, the DPV signal has consistently increased. At the same time, using the same released nanoparticles, TMB was oxidized, and the optical signal using the UV visible, we could monitor the optical signal. So again, similarly, both optical signal and electrochemical is being obtained using the same methodology which we are developing. However, we had a beautiful observation that the electrochemical signal, being more sensitive, could able to detect from 10 femtogram. However, and using the optical methodology, we could reach until 100 nanogram. So in this case, using the dual modality, not only helped for the dual confirmation of the signal, but however, it extended the linear calibration of the detection methodology. So this is the advantage of combining two different methods into one methodology, like getting two different signals from one methodology. We can also get the dual confirmation. At the same time, we could also get a linear increase in the calibration curve. So we can detect more sensitive virus here in this case. Now, going further, after doing these two works, what we could determine was, we clearly observed that calorimetric method is easy for detection because it can be visibly seen. However, the fluorescence method was more sensitive method. Sometimes with the working methodologies, we could also reach PCR level of detection. But however, optimization is crucial step in the sensing. And in other cases, like some limitations and probable overcomes, we saw that sensor development is actually a very difficult step. And because a few number of viruses can be lethal, which is difficult to detect. So there is a necessity for higher sensitivity. Coming to other observation, electrochemical sensing or dual sensing was more advantageous than the existing methods because they are highly sensitive using the electrochemical, and we can increase the reliability of the developed methodology because we get two different signals. Though one has a false positive, there is an chance that in the second one we could get good signal. So if both results corroborate to each other, then only the result could be published, and getting into the double checking. So using the dual sensing, this all could be obtained. However, we further understood that these are all existing methodologies. Just combining two methodologies was not very advantageous. Like in the present pandemic situations, if we can develop even more sensitive detection methods using more sensitive signals, it would be much better. At the same time, there is a necessity for developing a point of care device in which even the power source could be obtained. So further, we made a few initial beginning steps for developing some kind of sensors, like in which what we have done is we have used the water oxidation principle. This was the first time wherein we have used the water oxidation principle for the virus detection. So as getting into the brief introduction of water oxidation. So in water oxidation is this nanomaterial, several nanomaterials are known to have some catalytic activity, and they have made considerable progress in analytical electrochemical field. Like for not detecting for virus, but in several other fields, people have been using the catalytically active nanomaterials. Now, getting into the water oxidation research, it is actually a catalytical oxidation of water molecules in the anode of the electrochemical, in the anode as part of the electrochemical water splitting. Like generally, when we use electrochemical, say we have both cathode and anode. Now, when the water is oxidized in the presence of the catalyst, that is the electrocatalyst, both oxygen and hydrogen gas can be generated at two different anode and cathode of the electrochemical cell. Now, here how the reaction can be monitored is what we are using. So this reaction can also be electrochemically monitored using some simple electrochemical techniques. And also these signals are more sensitive. Like, let me explain you more detail about the things. So here what we have done is, initially we wanted to develop a electrocatalyst which has the ability for the water oxidation. So we know that platinum is a well established material, but however, though as platinum is very expensive and not easily available, it is always good to combine with some metal oxides for more stability, increased activity and all. So we tried to synthesize platinum and cobalt oxide, platinum conjugated cobalt oxide hollow cages. So for the synthesis, what we have done is, we have used the MOF, the metal oxide framework. So here what metal organic framework. So here what we have done is, initially methyl imidazole was precipitated with cobalt ions, forming the ZIF67. So this is a compact structure, whole structure. Then we have separately synthesized the platinum nanoparticles with PVP coating, and we have conjugated them to this ZIF. Because of the organic linkers present on the ZIF67, because of the organic linkers, the PVP coated platinum nanoparticles could covalently attach on the surface of the ZIF67. Then upon pyrolysis, using the thermal decomposition, the organic linkers were removed and also the cobalt ions were oxidized, resulting in the formation of platinum conjugated cobalt oxide hollow cages. So we have done the synthesis here. Like here, we have done some TM of the synthesized nanomaterials, where we can see when the material, when the platinum coated ZIF is a complete structure, like it's a whole structure with around 400 nanometers of size. Now, when after the pyrolysis, that is the thermal decompositions, after the removal of the carbon and organic linkers, we could see the hollow structures being formed, like several small particles like cobalt oxide or platinum nanoparticles forming a cage-like structure, the hollow cage-like structure, which can be clearly seen in this image. The size was around 200 to 250 nanometers of size. Then after successful synthesis, we wanted to know if platinum is incorporated or not into these nanomaterials. So we have done the imaging mapping. So wherein we could see cobalt, oxygen, and platinum, three have consistently existed together in the same regions of the nanomaterials. So this, like if we see here, the depth of the materials is very high. So in the images as well, we could see high amount of loading of cobalt, oxygen, and platinum. So this confirmed that our synthesized nanomaterial was containing cobalt, oxygen, and platinum, which confirmed the synthesis of nanomaterials. Then to further elucidate the functional properties and functionalizations present on this nanomaterial, we have further performed some other characterizations like XRD, wherein we could see, like if you can see the cobalt oxide, the blue color peak, XRD, we can see the peaks at around 18 and 31 and 30, 32 and 45, which are the strong crystalline peaks of cobalt oxide. After the conjugation of platinum onto the cobalt oxide, we could see a new peak has arisen around 38, which is attributed to the incorporation of the platinum nanoparticles. So this gave an indication that platinum nanoparticles are incorporated onto the cobalt. And in further, we can see, though platinum nanoparticles are incorporated into the cobalt oxide structure, the peaks of cobalt oxide have not been distorted. So that means that they are still maintaining their original structure. Now further, surface area. Surface area analysis is very important for electrochemical reactions, because higher is the surface area, high is the chance for the interaction of the electrolyte with the nanomaterial, that is the nanocatalyst. So the electrochemical activity could be high. So we have done the BET analysis using the nitrogen adsorption desorption curve, where we could obtain the surface area of around 70 for the prepared nanomaterial. Along with, we have done the pore size analysis, where we could see beautiful mesopores present on the surface of the nanomaterials. Now further elucidate the further properties of nanomaterials, we could see we have performed the XPS of platinum, where we have deconvoluted the platinum and cobalt oxide, where we could confirm that the prepared nanomaterial was beautifully synthesized with all the necessary functionalizations. Then after successful synthesis of the nanomaterials, we wanted to use this material for water oxidation. So we have initially characterized the material for water oxidation principle. So what we have done is, initially we have done the cyclic voltammetry, CV. wherein we can see here blank is the SPC, that is screen printed carbon electrode, only carbon electrode, wherein we could see a small increase in the potential at around 1.5. From here around 1.25, small increase, but it is very less. When only ZIF67 was added, a little shift is observed, but not very much. But however, when cobalt oxide was added onto the surface of the SPC on the screen printed carbon electrode, the current consistently increased, further shifting, positive shifting of the potential. At the same time, when platinum cobalt oxide was added, the shifting has further occurred, showing the prepared nanomaterial of platinum cobalt oxide halocages were more electroactive. Now, to further understand the mechanisms, we have done the electrochemical impedance spectrophotometry, EIS, the electrochemical impedance spectra, wherein we can see only for the synthesized cobalt oxide, the charge transfer resistance was little high, and it decreased drastically when the platinum was incorporated because of the metallic property of the platinum. So the charge transfer resistance decreased and the conductivity has increased very high. However, when antibody was coated, anti-HEV was conjugated to this platinum cobalt oxide for doing the sensing performance, the conductivity decreased a little, and the charge transfer resistance increased because of the conjugation of the biomolecules onto these nanoparticles. Now, after successful optimizations of this method and understanding the potential of 1.35 was good, we further performed the chronoamperometry, which is a very good method to understand the water oxidation reaction. Like what happens is, so what we have done is we have taken different concentrations of the nanomaterials and we have deposited them, known concentrations of nanomaterials, and we have deposited them onto the electrode, onto the screen printed electrode, carbon electrode, and we have performed the chronoamperometric study for around 200 seconds, wherein we could see with the increase in the concentration of the nanoparticles, the current has consistently increased. The current values have consistently increased. Like in the case of 1 nanoparticle, the current values were very small. But when the nanoparticles increased to 40 nanomolar or something, the current values consistently increased. And here we can see initially a drastic decrease in the current value from very high because of the rapid activity of the water oxidation on the surface of platinum. But it further maintained a consistency, and we can see the signal was little deviating, like ups and downs until 150 seconds. But at 200, we could obtain a stable signal. So we determined that 200 seconds was the better signal for the analytical optimizations. And also we could get a linear calibration for the different concentration of the nanomaterials and the current values. Now, using this methodology, we have developed using this, because here we can see 1 nanomolar of nanoparticles could generate some signal in the water oxidation principle. Using this principle, we again developed a virus sensing methodology. Here, if you can see in this part, what we have done is, first we have prepared the nanoparticles, antibody coated nanoparticles, and also we again used the magnetic nanoparticles with antibody coating. What we have done is we have mixed the virus particles as well as magnetic nanoparticles and the cobalt oxide antibody coated nanoparticles into the mixer. We mix them together and allowed them to conjugate to each other. And after the successful conjugation, formation of the sandwich structure between magnetic nanoparticle, virus, and cobalt oxide nanoparticles, they were again magnetically separated to decrease the interference of the for other sample. So going ahead, what we have done is, after separating this matrix, these nanoparticles which are separated were deposited onto the electrode. So only if virus particles is present, the platinum coated cobalt oxide particles are coming. In the absence of virus particles, only the magnetic particles would be separated. As in here, we can see magnetic nanoparticles, virus, and cobalt oxide nanoparticles. So after depositing,
excuse me, doctor. Excuse me. You have two more minutes.
Yeah,
including the discussion.
Yeah. Okay.
Yes.
So with the increasing concentration of the virus-like particles, we could get linear calibration curve as seen here. So now we have also further performed in serum and real samples, and we could get good linear calibrations. And further, we have performed the selectivity using various viruses like norovirus, Zika virus, WSSV, influenza, H1N1, H3N2, and we could see good selectivity because of the attached antibody. So this determined very sensitive virus detection could be possible. Now, coming to the conclusions, we have developed several new class of nanomaterials for developing various virus sensing approaches. We have also developed dual modality calorimetric fluorescence electrochemical readout based sensors, and we synthesized a new class of nanocomposite like platinum cobalt oxide hollow cage, which was very excellent electrocatalytic material for water oxidation, and we could detect HEV in a very good linear range. And further, I would suggest that using some advanced methodologies like OER, combination of OER and HER can be applied for virus sensing. These would be the new works which can be done. Yeah, and thank you very much for your kind attention. And this is our group. We are working together here. Thank you very much.
Thank you very much. Thank you very much for very nice, interesting work. And I'm not so much familiar with this field, but I'm very much impressed your work. And maybe this is very promising work. I think this is very important to sense the virus itself.
Yeah, thank you very much for your comments.
Is there any questions from audience? It's almost time is coming, but if there is short question, then no. I'm very much interested in your work, and I have many questions, but just one. In the former part, the detecting the virus, if you choose the appropriate antibody, then you can distinguish many kinds of the virus. And I may miss, but did you say that is there any limitation of the such distinguishing of the virus, or you can distinguish any kind of virus?
Yeah. So, Professor, here actually coming as we are working as a chemist. We are working as a chemist, so we are not working on the biological parts. So the selectivity, whichever is being obtained in our developed methods, is from the antigen-antibody interaction.
I see.
We are completely believing on the antibodies for the selectivity of the virus detection. So what we are majorly developing is the amplification systems. So how sensitive we can detect using the nanomaterials and the nano methodologies which we are developing. So the selectivity is completely being obtained from the antibodies being used.
I see.
Yeah, and as a biologist, as several biologists say, these antibodies are very specific for the virus. Several antibodies would be very specific for the virus. So that is the reason we could get a good specificity in several cases.
Even mixed with many kinds of virus, but you can choose one of them.
Exactly.
Yeah, I see. Okay, so any other questions? Otherwise, the time has already passed, and let's thank the speaker again. Thank you very much for the interesting, nice lecture. Thank you very much.
Thank you.
So,
yes, sir.
Is this the end?
Yeah.
The end of all the lecture schedule? Yes.
Yes. Behalf of the organizing committee and the chairperson, I heartfully thank all the invited speakers for the excellent research contributions to our society, as well as the research works presented in our these technical sessions. And I thank the chairperson, Professor Shikamoto, for chairing this session in a great manner. And I finally thank all the active participants who have participated in these technical sessions. Thank you so much.